Guys, if you're around, you just let me know. If you are around, just call my attention, please. If you are in the house, call my attention so that we can commence our discussion. Uh, where are you? Excuse me. Augustine. Pablo. Hello, how are you? Morning. Please, Augustine, where are your guys? Where are your guys? Did you not tell them about the life? Did you not tell them about the life? Send the link to Fidelis and Francis. Francis and Fidelis, if you have joined, please just give me a signal. You can say Francis and Fidelis, if you have joined, please give me a signal. Francis and Fidelis, if you have joined, give me a signal. Give me a signal, please. Yeah, Fidelis, I wish you the best. How are you? How are you? What about Francis? Fidelis, I hope you enjoyed your break. Augustine, you guys enjoyed your Easter, right? I hope you revised what we did already. Remember, we don't have much time. So today there's no time. What we are going to look at is mathematical truth and certainty. So we'll look at why mathematical truths are always certain, and we'll explore the views of Platonists and Logicists. And there are many schools of thought in the philosophy of mathematics. So today we look at mathematical truth and the certainty of mathematical truth, and we'll explore the views of two schools of thought regarding mathematical truth and its certainty. So the views of Platonists and Logicists. From logicists. We are going to review them today. Yeah, Francis, welcome. Francis, welcome. Now, if you remember what we did earlier on when we were talking about mathematics and the features of mathematics, we mentioned some of the remarkable features of mathematics, and we said that certainty and reliability are one of them. That one of the quality of mathematical truth, mathematical fact, mathematical knowledge is that it is certain, it's reliable everywhere, it's universal. So what is correct about mathematics in Nigeria is correct in Asia and is correct across Africa and other parts of the world. So that when you say 2 plus 2 equal to 4, it is certain, it's precise, it's distinct, it is truth everywhere, it cannot be denied. So this is one of the distinctive quality of mathematical truth, unlike scientific truth, which sometimes can be questionable, it can be refuted, it can be discovered not to be true in some places. That's why in scientific truth we have what they call constant. They tell you that given a particular condition, this is bound to happen. But mathematics, there's no condition. It is 2 plus 2 is 2 plus 2 everywhere, regardless of the condition, whether there is high temperature or low temperature, whether the atmospheric pressure is low or high, on the mountain, on the valley, in the ocean, anywhere, 2 plus 2 is always 2 plus 2. So this is the most distinctive quality of mathematical truth. It is certain, it's distinct, it is undeniable, it is irrefutable. So, but philosophers ask questions regarding this. So why are mathematical truths so certain? Why? What is it in mathematics that makes the truth of mathematics irrefutable, so certain that it cannot be denied? What is it that makes mathematical statements necessarily true? Because they are necessarily true statements, and that is why they are indubitable. Because the necessary statement is a statement that cannot be denied, it's indubitable, it's irrefutable. So why are they always true? Why are they necessarily true? Why are they necessarily true? Remember when we did deduction and induction, we told you that while inductive arguments or reasoning or conclusions are not necessary truth, that deductive are necessary truth because they are demonstrative, they are demonstrated, the truth of the statement proceeds from within the argument, from within the premises that are presented as logical reasons for the conclusion. You get? So mathematical knowledge has that pattern of logical structure, and that is why it is always certain. It is a necessary truth. So what distinguishes mathematical knowledge from other forms of knowledge? Now, what I'm saying is this. In philosophy of mathematics, mathematics is established. Mathematical knowledge is established, is said to be always true. Right? It's true everywhere. It's certain. That is for mathematics. But in philosophy, we raise questions regarding this certainty. So three important questions arise. And the first one is, why are mathematical truths so certain? Why? The second one is, what are mathematical statements? What makes mathematical statements necessarily true? Because they are necessary truths, and you know by now you should know what we mean by necessary truth. Necessary truths are truths that may not rely on experience or experimentation to be proven. For instance, when you say a bachelor is unmarried, is a necessary truth. You don't need to go and find who the bachelor is before you know that. One, because the predicate is substantiated by the subject itself. You get? So, and the third question is, what distinguishes mathematical knowledge from other forms of knowledge? Because if we're able to discover the factor that distinguishes mathematical knowledge from other forms of knowledge, then we notice that in that factor therein lies the element of certainty in mathematical knowledge. So the study of these four questions I just outlined makes the discourse on certainty of knowledge in mathematics very, very crucial. So now what we are going to do is we are going to look at the nature of mathematical truth. It is related to what we did already when we were talking about the features of mathematics. But I will repeat it because it is very, very important here. It's significant, it's crucial in this case. Because regarding the third question we raise as philosophers, what distinguishes mathematical knowledge from other forms of knowledge? We have to look at important features of mathematical truth to find out the forms that distinguish mathematical knowledge, mathematical truth from other forms of truth. You get? And these features of mathematical truth, they are related or almost the same, if not completely the same, with the features of mathematical knowledge. Are you with me? Are you following me? I hope we are together. So it is not as if we are repeating anything. We are not repeating. The nature of mathematical truth is almost or even completely the same as the nature of mathematical knowledge. Because mathematical knowledge and mathematical truth, they are similar, they are the same. We are talking about the same thing. So both share the same relationship, the same features, because it is mathematical knowledge that births mathematical truth, or vice versa. That is, it is mathematical truth that births mathematical knowledge. So what features as a characteristic in one will ultimately feature as a characteristic in the other. I hope you understand what I'm saying. So one of the important features we are going to look at in the nature of mathematical truth is universality. I already explained this universality concerning mathematical knowledge earlier on, maybe in the previous weeks of lecture. So mathematical truth are universal. I've already explained. They are universally valid. What does this mean? This means that they are true everywhere, regardless of culture, location, or time. Mathematical knowledge, mathematical truth, they have this quality. And this is one of the factors, one of the forms that distinguish mathematical truth from other kinds of truth. They are universally valid, anytime, anywhere, any location. They do not depend on any form of circumstance or condition. Regardless of the circumstance, the condition, the time, the place, the occasion, mathematical truths are always valid. They are universal. They are unquestionable. So that, for instance, when you say 2 + 2 = 4, is universal. So you can even say that mathematical truth is a universal language. It is, because it is comprehensible and acceptable everywhere and every time. Then the second important feature of mathematical truth is they are necessity, they are necessary truths. I've explained this thing is just to give it itemization so that to itemize it or to be more specific so that you can grasp it more easily. So they are necessary truth, necessity. Mathematical truths are necessary truth. A necessary truth is a statement that cannot be falsified. That's what necessary truth is. Is a statement that cannot be proven false. Like the example I gave you before. The example I gave you before, I said, you remember when you did Kantian logic, you talk about a priori truth and synthetic a priori truth. When you say that a bachelor is unmarried, it is a necessary truth because the statement cannot be falsified. Because once you mention bachelor, a bachelor within the subject, the predicate is substantiated, is clarified, is validated. So it's a necessary truth. In mathematics, for instance, every mathematical proposition, for instance, you say that a straight line is the distance between 2 points. For instance, it's a mathematical proposition. It is valid everywhere. Once you have 2 points, you can always draw a line that will link both of them. And that line should be straight. It is a distance. Okay? Then when you say 2 plus 2 equal to 4, it's a mathematical proposition. It's a necessary truth because it cannot be falsified. 2 plus 2 equal to 4 cannot be falsified. Because if you split the 4, you must find double 2's. Even if you want to say that you can make another relationship that will give you that product. For instance, when you say 3 plus 1 equal to 4, or when you say 5 minus 1 equal to 4, yes, it's correct, but it does not invalidate the fact that 2 plus 2 is still equal to 4. I hope you are following me. Please, if you understand what I'm saying, just give me a sign. Just say yes, 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 yes. If you don't understand, let me know that I'll go back. If you understand what I've been explaining so far, just say yes. Say yes. Let me see your reaction on the comment section. If you understood what I have been saying so far, please react. I don't want it to seem as if I'm speaking to myself alone. Okay, good. Okay, good. So remember, I have said it that mathematical truths are necessity. Necessity means that what? They cannot, a necessary statement is a necessary truth is a statement that cannot be falsified. And mathematical knowledge, mathematical propositions have that structure. They cannot be invalidated, they cannot be falsified. Then, exactness and precision. You notice that, like I said earlier, it's as if we are repeating the other features. Not all of them are the same. There are new ones here, like necessity is not in the first one. But exactness and precision features as both a quality of mathematical knowledge and mathematical truth. Okay? The same thing with universality, but necessity doesn't feature as a quality of mathematical knowledge, but it features as a quality of mathematical truth. So, exactness and precision. What we mean here is that mathematics is extremely precise. It's extremely precise. Mathematical truths are extremely precise. Mathematical statements are clearly defined and they leave no room for ambiguity. They are very, very clear. Remember, they are distinct. And if you remember, like I said earlier in one of our meetings, this exactness and precision is one of the inspirations that early modern philosophers like Descartes, René Descartes, Francis Bacon, and the rest of them, that made them to begin to go in search of a philosophical method that can allow philosophy to come out with knowledge that is as precise and distinct as mathematical knowledge, because they were inspired. So they wanted a method in philosophy that can ensure a similar level of certainty and precision, exactness, distinctiveness that is enjoined, that is assured by the method in mathematics. So exactness and precision is another significant attribute of mathematical truth. They The mathematical truths are free of ambiguity. They are not ambiguous. Mathematical truth, mathematical statements are always distinct. They are always distinct. Every mathematical proposition is defined. They are they are they are always free from ambiguity. They are clear, they are precise, they are distinct, they are exact. Um, so, for instance, when you say you make a statement like such as above 5 is vague, that's not mathematical statement. Above 5 is vague, but when you say 5 is precise. 5 is precise. Okay? Then, logical structure. Logical structure. Mathematical truths are based on logical structure. They are derived through a sequence of logical steps known as proofs. If you remember in your earlier levels of education, when you do um, um, long mathematical operations like maybe LCM or even HCF or even quadratic equation or simultaneous equation, there's what we call pure ED, quad errand demonstrator. You see that sometimes they will tell you to prove something. You follow a logical order of explanation to solve whatever equation, whatever operation is given to you. And at the end, some of them, you have to write proved. Okay, so you discover that all the steps you follow to arrive at the answer, the solution to what you are solving, they are logical. So you discover a structure so that if you miss one, you may not be able to arrive at the right conclusion. And even if you arrive, your examiner will tell you wrong step. So what it tells you is that there's a logical structure. There is a logical structure that is followed in order to arrive at the conclusions or the solutions of mathematical problems. So every mathematical truth follows a logical structure. And this logical structure ensures that the procedure and the method is the same everywhere, so that another person can follow the same logical structure, or different people can follow the same logical structure across different divides in the world and still arrive at the same solution. So these four qualities are very, very important as defining qualities of mathematical truth. These four, we have mentioned four: logical structure, exactness and precision, universality, and necessity. They are very, very important. They are very, very important as distincting and as defining features of mathematical truth. And these defining features are the features that separate mathematical truth from other forms of truth. These defining features are the reason why mathematical truths are always certain. They are the reason why mathematical truth is different from scientific truth, because scientific truth may not be certain always. Sometimes they can be fallible, but mathematical truths are not, and they are infallible. You get? So these features we just mentioned, these four features, are the forms that distinguish mathematical truth from other forms of truth. They are the forms. Now, let's talk about mathematical proof. Mathematical proof, Proof. Mathematical proof. Now, what is a proof in mathematics? A proof is a logical argument. I explained it earlier on. Is a logical argument that demonstrating the fact that a mathematical statement must be true. So a mathematical proof is a logical argument that demonstrates the fact that a mathematical statement must be true. So when you are given you are given 2 plus 2 equal to 4. They say prove it. The statement is already true, but they expect you to make an argument to prove the truth of that statement. So whatever you do following a logical structure, you are trying to show that yes, that mathematical statement is true. And once you show it through the logical argument you present, through the steps you present, once you show it, you have proven it. You have presented the proof. You can now end by writing cure ed, quod errand demonstrandum. So a mathematical proof is a logical argument demonstrating that a mathematical statement must be true. The statement is already true, but they want you to prove it. To prove it is to show, to present argument, to present steps, to present orderly steps, a step-by-step operational procedure that will end up showing why when you put 2 and another 2, it will give you 4. Okay? So, how do mathematical proofs usually begin? They usually begin with what we call axioms. Some of these terms I'm mentioning, they are very, very important. They usually begin with what we call axioms. And what are axioms? Axioms are basic principles that are assumed to be true. They don't need to be proven. They are generally accepted principles. I will still explain what axioms are usually. I'll explain it better because we have it as a sub theme in the course of the lesson of the class. So mathematical truths usually, if you want to prove a mathematical truth, usually begin with axioms. So axioms are statements that everybody accepts as true. So you begin from the known to unknown, right? Then definitions. You also use definitions. Definitions are precise explanations of mathematical concepts. Axioms are basic principles that everybody accepts, generally accepted to be true. They are not questionable, right? Then definitions. Definitions are explanations of mathematical concepts. Definitions are ideas that are definite. That's why they are called definitions. They are definite. They are exact. When you define something, you are establishing the exactness and precision of that thing. Now from these are the two starting points when you are trying to prove anything mathematically. When you are trying to present a proof mathematically, you begin with axioms and definitions, because these two they establish the standard you can proceed. Because when you state axioms, it's something that everybody knows. If you state definition, it's something that everybody knows. So if you state the axiom, it's just like stating premises in deductive and inductive argument. If you state premises, everybody knows it. So, but from those premises, you arrive at a conclusion. That's what axioms and definitions also do when you are trying to prove mathematical knowledge, mathematical truth. You state what everybody knows. You define it, and from there you proceed to using it, right, to establish the fact of what you have been given to prove. So you can, in essence, compare axioms and definitions in mathematical proofs. You can compare them to premises in syllogism, because axioms and definitions almost function in the same way that premises function in syllogism. What I'm saying is that the way axioms and definitions function in a mathematical proof is similar, very similar to the way premises function in syllogistic argument. I hope I'm communicating. So just like premises are the starting point in syllogism, when you are drawing or making a syllogistic argument, that is how axioms and definitions are the starting point in mathematical proofs. Okay, so you state the axiom, define, state your definitions, and from there you proceed to establishing the proof. The same way in syllogism, you state the premises, and from the premises you proceed to establishing a conclusion. Okay, so the premises are in syllogism are similar to the axioms and definitions in mathematical proofs, and the conclusions in syllogism are similar to the what? To the fact that is proven in mathematical proofs. Now let's look at what these axioms. I just pray you understood my explanation of axioms already. To give it more flesh, because sometimes you see axiom, you don't even know what you're talking about. So an axiom in science, in mathematics, even in philosophy of science, wherever I see it, is, I've said it already, is a statement that is accepted as true without proof. In mathematics, in philosophy, you can call that a priori statement. You can even make it more qualitative when you call it synthetic a priori statement. In mathematics, that a priori statement are statements that, or synthetic a priori statement in the language of Kant, are statements that the subject and predicate establish the fact, the validity and truthfulness or worth of that statement. So you don't need experience or experimentation to guarantee the validity or truth. In mathematics, what we call those kind of statements are axioms. Statements that are accepted as truth without any kind of proof experimentation. For instance, you say a line is a distance between 2 points. You don't need any kind of experimentation to prove that. You don't need any kind of experimentation because it is given. Once you have 2 points, there must be a line between them. And you can also say that what the distance is the space between 2 points. You don't need anything to prove it, because within these are axioms, because within the statement already you are saying the fact. You say what goes up comes down is a mathematical statement. It's scientific. Even is beyond scientific. Is axiomatic. You don't need any kind of experimental. Once you see everything, you see it daily happening. Things go up and come down. Things go up, come down. They go up, come down. Of course, except in the case of aeroplanes or when the force of gravitational force is defeated. But things generally go up and come down. These are axioms. These are mathematical statements. They are statements in mathematics that do not need proof before they are accepted. They are generally accepted statements that do not need any kind of proofs to be presented. When you make any statement in mathematics that is acceptable generally without any form of proofs or experimentation necessary, is what we call axiom. So axioms, like I said already, they serve as the foundation of mathematical systems. If you are given anything to prove in mathematics, whether simultaneous equation, whether whatever, you begin with axiom. You state the given. You state the given that this is equal to this. If, for instance, if you are given a simultaneous equation or any of these, they tell you find x, find this. Or, okay, let's say, okay, let me use this simple one we used to do even in primary and secondary school. They tell you that a boy bought one book. Listen very well. A student bought one book for $10. Listen. A student bought one book for $10. How much will 100 cost? What do you do there? If you want, this is a proof. Okay, or okay. How do you proceed if you want to solve this kind of? You begin by stating definitions. One of the definitions there and the axiom there, let's use axiom here, is that one book costs what? $10. So you go and state one book costs $10. That's an axiom, and it's also a definition. You proceed from there. So it's they underline and even underlie the foundation for every mathematical proof. So if you are beginning any journey in every mathematical operation, no matter the kind, you have to begin with axioms and definitions. So when you state one book costs $10, you begin from there. If one book costs you go from there, you proceed to definition. 2 will cost what? 2 will be equal to 2 times 10, right? Which will be equal to $20. Then you proceed to the conclusion. Therefore, 100 will cost what? 100 book will cost what? If to get the solution to 2 books, you multiplied the cost of one with the amount, with the number of books you want to buy. It also means that what? To get the cost of 100, you have stated that second definition based on the axiom that was given to you in the mathematical question. So from there, you proceed to say that what? 100 will therefore equal to what? 100 times what? 10. And that will give you what? $1,000. So you can see the function of axiom and definition as standard procedures or steps in every mathematical proof. I hope you are following me, please. I hope I'm not speaking I'm not speaking in tongues, or I'm not saying things that are too wild or beyond your experience or capacity to understand. If you are following me, please just say yes. Say yes. Let me see. If you are following me, please. If you have been following and you have no confusion, just say yes. If you have been following me, let me see your reaction, please. If what all I have said so far has been very, very clear, let me see your reaction. Your reaction. Okay. Augustine says yes. Fidelis, is it clear? Augustine, is it clear? Okay. I guess you are with me. I guess it's clear. Okay. So I need you to be able to understand what axioms are. I have used different elements in philosophy, deductive arguments, syllogism, and so on, to help you demystify what axioms are and definitions. And remember, we have pointed out that what axioms and definitions are standard takeoff procedures necessary to prove the truth of every mathematical operation. So they are very, very important. They are the state and determine the standard to any proof you want to establish in mathematics. Then the next thing we are going to talk about is why mathematical truth appears certain. We have established some of these things before. So mathematical truths always appear certain because they offer different explanations for certainty of mathematics. You have logical explanation. This thing is, don't see it as repetition. They are related because you can, for instance, tomorrow if you are given a question to tackle to explain or establish why mathematical truths are always certain, you can come from different perspective. You can come from the perspective of, you can approach the question from the perspective of the nature of mathematical truth, pointing out the qualities of mathematical truth. You can come from the viewpoint of the one I'm about to do now, different explanations that has been provided to to a kind of substantiate, that's the right word, to substantiate why mathematical truths are always certain. So there are different explanations that have been offered by scholars across the years. So the first one is logical explanation. So why I am doing this, I don't want you to get it mixed up or jinxed or even, to get confused. There are different approaches to establishing the facts of the certainty of mathematical truth, and to say why, to explain why, to give reason why it is always certain. You can come from the viewpoint of the nature of mathematical truth, where you can mention the qualities of the truth: exactness and precision, necessity, universality, right? You can come from there. Then you can come from the one I want to do now, the different explanations that have been provided by scholars over the years. So you can begin with logical explanation. Some philosophers argue that mathematical truths are certain because they are derived from logical principles. They are derived from logical principles. Very much related to one of the features we mentioned when we talked about the nature of mathematical truth. We talked about logical structure. Essentially, what I'm doing now, a kind of substitution we have taken or we have explained. So logical explanation, some philosophers argue that that the reason why mathematical truths are certain is because they are derived from principles. They follow some logical standard of operation. They follow a logical structure. And because they follow a logical structure, they are always certain. So logical explanation, that's one of it. Then rationalist explanation. This is the viewpoint of some rationalist scholars, philosophers, who argue that mathematical knowledge always appear to be certain because they proceed from reason rather than experience. They proceed from reason rather than experience. So because they proceed from reason always prevails over experimentation and experience. Because when you talk about experience and experimentation, you talk about sensation. Perception can be very, very confusing, because if you talk about perception, sensation, experimentation, people's perspective comes to play. Perspective becomes a rationalism. Relativism. And when relativism comes in, it can bring to question the certainty of whatever you are trying to prove. But these guys are saying that the reason why mathematical truths are always certain is because it is not based on experience or even experimentation. It relies on reason. It is derived from reason. And because it is derived from reason, it is difficult to say that it's not certain. So for them, mathematical truths are certain because they are based on pure reason. They are based on pure reason. And remember Kant's critique of pure reason. No matter how he tried to criticize it, he still came to synthetic a priori conclusions, which is still founded partly on pure reason. So I've talked about logical explanation, and rationalist explanation. Logical explanation regarding the certainty of mathematical truth, it is not the same as rationalist explanation. Logical explanation says that mathematical truths are always certain because they follow a logical structure. They follow a logical structure. Logical structure means step-by-step procedure that are indubitable, that are expository, that determine what the conclusion would be. Just like you have in syllogism, where you have premises and conclusion. You have first premise, second premise, if you like, third, fourth, till you arrive at the conclusion. So in mathematics, logical explanation is because mathematical truths follow that same logical structure. That is why they are always certain, because the structure gives a kind of durable and unshakable foundation to the conclusion, right? But in rationalist explanation, what they are saying is that that mathematical truths are considered to be always true because because mathematical truths are what? Are based on reason, pure reason. They are not the same thing, please. They are based on pure reason. Pure reason means that what? They are almost totally taken from what? The rationalization of the individual. They are not based on experimentation or experience or perception. They are grounded on reason, pure reason, for emphasis. I hope you are with me. Then there's another explanation, Kant's explanation. Kant's explanation is like a rationalist explanation, but is for emphasis we have to talk about him because he's a major proponent here. The philosopher Immanuel Kant argued that mathematics provides synthetic a priori knowledge. Remember Kant, right? He talked about a posteriori knowledge, a priori knowledge, and synthetic a priori knowledge. Right? A posteriori knowledge, knowledge that is based on experience. A priori knowledge, knowledge that is not based on experience. Synthetic is his reconciliation of the two. A knowledge that is partly based on experience and partly based on what? And that is not, and that is partially based on experience and partially based on reason. That is gotten both from experience and reason. So according to Kant, mathematical truths expand our knowledge, and that's why I call it synthetic. They are known independently of experience. They are known independently of experience. They can be known independently of experience, but yet they are still founded in experience. They can still be proven by experience. That's why he said that what? They are synthetic a priori knowledge. For Kant, mathematical knowledge are known independently of experience. They are known independently of experience. That is, they are based on reason. Yet, they can rely on experience to be proven. That's why he called mathematical knowledge synthetic a priori knowledge. So he believed that the structure of the human mind makes mathematical knowledge possible. The structure of the human mind makes mathematical knowledge possible because the human mind can come to the knowledge of things intuitively through rationalism, through reasoning. At the same time, the human mind can fall back on experience to give added value to what it has intuited based on innate knowledge. So the human mind has that quality to be able to know things based on experience, based on reason, and also to be able to fall back to reason in order to give more validity and substance to what it has come to the knowledge of through intuition, through reason. So, different explanations, theoretical explanations to why mathematical knowledge appears certain. I've just talked about logical explanation, rationalist explanation, and then Kant's explanation. Okay? I hope it's clear enough. Now, before we leave this section, let's look at the difference between mathematical knowledge and scientific knowledge. They are not the same thing. Mathematical knowledge and scientific knowledge, how do they differ? They are not the same. Mathematical knowledge versus scientific knowledge. What is the difference between the two? How do they differ? Sometimes scholars and even students think or suggest or erroneously conclude that mathematical knowledge is the same as scientific knowledge. No, they are not the same thing. They are not the same. The distance between the two is as far as from Africa to Europe or even America. They are not the same. They are miles apart. So they are not the same thing. Now, how do we differentiate the two? They are related, but they are not the same. So mathematical truth differ from scientific truth in several important ways. One, mathematical truth is based on logical proofs. Mathematical truth, they are based on logical proof, while science is based on observation and experiment. So science hardly submits to reason. You must show reason experientially, pragmatically. It's based on experience, experiment, observation. But mathematical truth can also, even though it can be based on that, but it is ultimately founded on logical proofs. That is one of the strong lines of demarcation between the two. Why mathematical truth is based on logical proof, the ability to follow logical structure. Scientific truth is based on observation and experiment. You must show working. You must be able to experiment whatever you think is true for you in science. You must be able to experiment. You must be able to prove it in the lab, in the workshop, using experimentation before it is accepted as science. And that's the essence and the importance of scientific hypotheses, theories, and laws. You have these two in mathematics, but unlike science, where these theories, hypotheses, and laws are based on experiments and observation, in mathematics they are based on reason and logical structure. Then another point of difference is mathematical knowledge are certain and necessary. I've explained what this necessary means. You should be used to it. You should. Mathematical knowledge, mathematical truth are certain and necessary. It means that what? They are indubitable everywhere. They cannot be proven false, even with or without experiments. Okay? Why scientific truths are often provisional and revisable. You get? Mathematical truths are certain and necessary. In fact, you can say they are internal, they are eternal, because they are from year to year, decade to decade, century to century. They are established because they are founded on reason. 2 + 2 = 4 is eternally so. But scientific truths are not that way. They are not as durable, or if you like, long-lasting or everlasting as mathematical truth. They are provisional and they can be revised. They are revisable. And that's why you talk about improvements in science and technology. Today, you have look at what we do in iPhone. I don't know what brand we are in now, what version we are in. 11, 12, 13. You see improvements due to growth in findings, more discovery. Check the human civilization, which is always a product of science, of course, and mathematics. But you see that there's this trajectory in scientific proof that after discovery is made, another greater one is made. So the conclusions are revisable, they are revisitable. So they are provisional. They are not certain and necessary. They are not. Nothing is perfect in the world, but if there's any kind of truth that is perfect, is mathematical truth. In essence, why scientific is provisional? Because a new scientific finding, can lead to change and further improvement in scientific knowledge. But in mathematical knowledge, because they are axiomatic and defined, it's almost impossible, if not impossible, to have further improvements in a particular mathematical statement or truth. It's not possible because it's definite, it's axiomatic. Then mathematical knowledge does not depend on empirical evidence. It does not depend on empirical evidence. It does not. I've said that already, because they are based on logical structure and they are based on rationality. They are axiomatic. They are definite. It does not rely on empirical evidence. But scientific truth rely heavily on um, on evidence, right? They rely heavily on evidence, and that is the essence of the experiment. If you are told to prove something mathematically, you are not told to go and bring evidence from outside or from the lab. It is theoretical proof based on rationality, based on logical structure. But for science, if you are told to prove scientific truth or fact, you have to go to the realm of experience. You have to go to the lab. You have to go to the lab, go to where you can do observations, and from the observations you come with an evidence to substantiate the facts you made earlier on. But in mathematics, no, you just do what you make recourse to axioms and definitions, and from those axioms and definitions you draw conclusions to establish the validity and truth of the statement you have made. All right, that's for that. So for instance, what we have just said is that what why scientific theories may change with new evidence, right? Mathematical truths, why scientific theories truths may change with evidence. Mathematical truths theories remain permanent and valid. They are permanent, they are valid. Go and check all those geometric theories. They are the same. Theories of longitude and latitude, pairing, they are the same. Pythagoras theory. Do you know when Pythagoras proposed or propounded the Pythagorean theory? Ages, decades, many BCs, thousands before Christ, hundreds of years before BC, before Christ. It still stands till today. It's the same. Go and check. You hardly find any scientific theory that have lasted that way. You have and that's why there are a lot of debates in scientific theories. But the mathematical theory is fixed, is stable. It's stable. All right. I don't know whether we can discuss Platonism in philosophy of mathematics today. I don't know, because in the spirit of langsam, so that I don't get your brain, overburdened. Is there any confusion? Because I'm done with the discussion on the mathematical, the truth and certainty of mathematics. I don't know. I would have loved us to look at theoretical positions, the viewpoints of Platonism and Logicism, but obviously we may not have the time. We will not have the time for that. So, gentlemen, any confusion? Otherwise, I ask you some questions to be sure that the lesson has been taken. Gentlemen, remember what I told you guys. Your assessment for this semester is not going to be based on term paper. You are going to do actual assessment. I'll give you question and you answer, and that will be the next time I come to the school. So what you need to do is these sessions we have been having online, you have to fall back to them. I think this is the third one we're having on philosophy of mathematics. You have to go listen, pay attention, because that assessment is over 30, if not 40, so that you don't score zero. So go back, take a listen to the lectures we have online, digest them. Each day you listen, if there's any confusion, drop a question there, make a comment. I'll always see it and reply, so that when you are confronted with questions in the exam or assessment hall, you will not have issues. Okay, Augustine, I've seen your comment. Fidelis, what about you? Fidelis, are you there? Francis, are you there? I hope everything said is clear enough. Is there any confusion? Is there any confusion? We'll leave Platonism and Logicism for next week. Is there any confusion? Fidelis, if you are still online, let me see you. Francis, if you are still online, let me see you. It's like it's only Augustine that is active here. Let me see you. Let me see you. Where are you? Okay. Let's see if you understood what I said. Can you what is the rationalist explanation for the truthfulness and certainty of mathematical knowledge? Was the rationalist explanation for that, and how does this rationalist explanation differ from logical explanation? Yes, react, please, react before we go. My question is, what is the rationalist explanation for the truth and certainty of mathematical knowledge according to logicians? Why is mathematical truth always certain, and how is this viewpoint of logicians provided in logical explanation different from the rationalist viewpoint? How? So I want you to tell me the rationalist explanation for the truth of science and mathematical knowledge, and tell me the logical explanation, and then differentiate the two. Please, reaction something online. Type, so that you can go prepare for your next session. Yes, I have not told you to leave the session. We are still here. I have not told you to leave the session. Where is Fidelis? Fidelis and Francis, where are you? Fidelis and Francis. Augustine, if you are there, react. If you are still there, I need you to react. If you are still there, I need you to react. React. Give me the logical explanation for the truth, for the certainty of mathematical truth, and tell me how this rationalist explanation is different from the logical explanation. Yes. If you are no longer there, I can just go, please, because I'm not seeing your reaction. Any reactions, or should we call it a day? Any reactions? I've always told you to ask questions if you don't understand, and I've always told you, if you are in the class during live streams like this, if you are asked a question, react, because your reaction will help me to see clearly what you know and what you are still confused about. Since I'm not seeing any reactions, I have to go. I'll see you. Probably tomorrow I may come to school. I don't know. If I don't come, we'll still meet online. But I'll see you when I see you. All right. Thanks for your time.